Welcome to Future Talk. My guest today is Jonathan Trent, founder and director of the Omega Global Initiative, which is developing new technologies to turn algae into oil while simultaneously cleaning up sewage water and producing a host of other environmental benefits. Jonathan has spent most of his scientific career doing research in microbiology, biochemistry, and nanotechnology. For the past 15 years, he's worked at NASA's Ames Research Center, where, among other things, he studied how organisms can survive in the most extreme environments on Earth, founded and led the Protein Nanotechnology Group, and won an award for his innovations in nanotechnology. He's also an adjunct professor in the Department of Biomolecular Engineering at the University of California, Santa Cruz, and he's an elected fellow at the California Academy of Sciences. He holds a PhD in biological oceanography from the Scripps Institution of Oceanography in La Jolla, California. I should also add that even though some of the initial ideas of the Omega project were developed at NASA, the Omega Global Initiative is Jonathan's private project, and he is not representing NASA on this program. Jonathan, welcome to the program.
Thanks, Marty. It's great to be here.
So what is the Omega Global Initiative really trying to accomplish?
Well, so the Global Initiative is sort of that second tier after we started the Omega project. Omega was an attempt to find a life support system for spaceship Earth. That is to say, a way to create an environmentally friendly system that produces energy, water, food, and does this in a way that is self-contained. And we've come quite a distance in doing that. And the Global Initiative is an attempt to find a place in the world where we can do Omega development even further.
Okay. And we're going to be talking a lot more about this, but before that, we have a video, an animation, showing what the Omega project is all about. Let's go ahead and roll that tape.
The project is called Omega. It's for coastal cities to transform solar energy into sustainable biofuels, electricity, and heat, to expand food production and access to clean water, to eliminate pollution and enhance the coastal environment. Ultimately, it's a project to develop sustainable green economies. Let me tell you how it works. Omega uses protected bays like San Francisco Bay, vast areas which will get even bigger with sea level rise. And most importantly, they already have wastewater treatment plants that currently dump wastewater into the bays. But for Omega, this wastewater is a resource, redirected into floating clear plastic tubes to grow microalgae, the fastest growing plants on the planet and the best producers of oil. The algae grow using nutrients in wastewater, and they use concentrated CO2 from a source like flue gas, which means Omega treats wastewater and captures and controls a major greenhouse gas. The Omega infrastructure is used for solar electricity and concentrated solar thermal. And in some locations, wave-powered generators and wind turbines will also provide power. In addition to energy, the Omega offshore platform supports aquaculture and produces high-quality food without using land and without using water. In fact, saving water is a big deal. It's estimated that by the year 2030, half of all the people in the world will face water shortages. And the current map of water scarcity shows in red that there are already many places in desperate need of clean water. Adapting methods developed for the space station for recycling water, Omega transforms wastewater into clean water using 1/3 the energy required to make clean water from seawater. Think about it. The integrated Omega components are modular, and they can be scaled up without using land. For example, the wastewater from one of the treatment plants in San Francisco will support a 1,280-acre Omega system and produce between 2 and 6 million gallons of biofuels each year. And what will be the environmental impact of a full-scale omega system? It will be like a huge kelp bed or floating reef that will provide a place for organisms to grow and forage, a refuge and nursery for fish and birds. So it is likely to increase local biodiversity and even enhance commercial fisheries. Omega improves the environment by treating wastewater and capturing CO2. It increases the availability of clean drinking water by recycling wastewater. It supplies food without competing with agriculture. And it provides solar energy as electricity, heat, and biofuels. All things that help move us toward a green economy and a sustainable society. If you want to find out more about what we've done already to prove the feasibility of Omega, watch my TED Global Talk or visit our Facebook page.
And that was our video of the Omega Global Initiative. So Jonathan, how is the initiative actually going? Do you have any working models of it yet?
Well, so the Omega project started within NASA and was funded by NASA and the California Energy Commission. And that project spent about $10.8 million in nearly 3 years to test all the working parts, to look at whether we could grow algae on wastewater and we could make these floating bioreactors and what would the details be. Now what we're trying to do is find a place in the world where we can deploy the first demonstration project. Where would be a protected bay that we can build this thing offshore? Because up to now, the Omega project has only been in tanks, seawater tanks, and in laboratory testing.
What would it take to find such a place? Somebody would have to let you build it there. What would be in it for them?
Yes, okay. Well, what we're doing is a kind of open source outreach. In the Omega Global Initiative, we're looking for places around the world. Japan, for example, is a really ideal location. Lots of protected inland seas, cities near the coast that are already dumping wastewater offshore, a real need for an alternative energy source given that what happened with Fukushima. All of these places around the world that we can think of where there's protected bays would be potential sites. What's in it for them is green technologies, or a blue-green technology, if you will, and food and a local carbon source a use of their waste streams into turning them into biofuels and energy.
It would be good if these places that had the farms would pay for them also, I assume.
Oh, yes, of course. Well, the concept of the Omega Global Initiative is that we'll provide information, and hopefully get local people excited about building this technology, but they would, of course, also invest in making the technology real.
We have a few slides that illustrate some different aspects of the Omega Global Initiative. Can we see the first slide, please? Okay, so this looks like an overview. Exactly what is this slide telling us?
Yeah, so this slide summarizes what we just saw in the video, that the Omega system is an integrated system, and that when we think about Omega in terms of energy from biofuels produced from algae, at the same time we should think of it as an infrastructure for solar power and potentially wind and wave, although solar and biofuels are really the best energy source. Because we're building an infrastructure offshore, we could build an aquaculture system using existing aquaculture technologies to make food. We've developed technology that allows us to recycle the wastewater as drinking water at 1/3 the cost that it would cost to make seawater into drinking water.
So the algae cleans the water that thoroughly that you can drink it after the algae?
The algae do the first stage, and then we use a combination of reverse osmosis and forward osmosis, technically, ways of making the water even cleaner. But the algae do the first step. And then finally, this has a positive impact on the environment. So as you can see, the environmental implications are really a crucial component of how the Omega system works. And when you think about all the implications of what I've just told you, that can have a huge impact on local economies.
Now, one of the important factors is the ability to transform algae into oil, because we always need more energy in our industrial economy. And we have a few slides that illustrate this, because many people might not know how algae becomes oil. Can we see the next slide, please?
And so this slide demonstrates, Marty, sort of how we grew algae in small containers to develop the tools for monitoring the growth of the algae and monitoring all the conditions within that environment where the algae are growing.
Okay, we have another slide which shows harvesting the algae. Like, how do you actually get the oil from the algae? So this picture here, what are they doing with the algae that's going to result in oil
So the big problem with these microalgae is that they're suspended in the water and we need to get them out. And the good news is that there's a lot of technology already existing for taking tiny particles out of water. And what this picture shows is how you can take these microscopic cells out of the water. And we concentrate them, and then we either dry them and extract the oil. I think that's shown in the next slide.
Okay, can we see the next slide? There it is.
And so there you can see the algae dried in that glass jar, and then we extract the oil either using a solvent or just by squeezing the algae and getting the oil out. Now, what a lot of people don't realize is that most of the fossil oil that we're currently harvesting from the deep earth or under the oceans came from these similar kinds of microalgae that existed 300 million years ago and were buried about 50 million years ago. And we're seeing the same kind of high production of oil from tiny microalgae that exists today.
So this is pretty much the same quality of oil that you would get if you drilled in the ground?
It's actually a better quality than oil, because a lot of what goes on in the ground at high temperatures and high pressures contaminates the crude oil. And we can make a kind of almost vegetable oil grade oil. The big problem is figuring out how to make enough of it.
Well, how big would one of these farms have to be in order to be economical?
Yeah, well, that's sort of the probably more than $64,000, probably many millions of dollar question. What we're looking for in the global initiative is building a demonstration project of about 1 acre. And that would be a proof of concept scale where, yes, indeed, we can get all the parts of the system to work at 1 acre, and it would be modular. And then we would iterate that 1 acre, making multiple versions of it. In San Francisco, the wastewater that's produced, as an example, is about 65 million gallons a day, which is enough to fill 1,280 acres of an Omega farm. And that 1,280 acres would make between 2 and 6 million gallons a year of biodiesel.
Now, does algae turn all of the wastewater into more algae, so essentially all the waste just disappears and is transformed into plants?
Yeah, so that's a really important question, Marty, because what the algae do is they not only extract the nutrients that are in the wastewater, which is the nitrogen and the phosphate and the potassium and many of the other elements, but it turns out that they also can treat the wastewater for pharmaceutical compounds. They remove caffeine, they take out the heavy metals. So they do really good things in cleaning up the wastewater. The Omega process takes that water 2 or 3 stages farther by treating the water using forward and reverse osmosis in a highly efficient manner that allows us to make this wastewater into drinkable water.
I think we have one more slide in this series of slides. Can we see that next slide, please? Okay, so this looks like a couple of specific elements. This will be a big array in the final farm, but those look like plastic tubes. So how is that really working? Did the algae grow in the tubes?
Yeah, so Marty, those are flexible, inexpensive plastic. It's linear low-density polyethylene. It's the same plastic we make greenhouses out of right now. Very UV-resistant plastic. It's very flexible. It's very inexpensive. And most importantly, lots and lots of it is available and can be made and recycled very effectively. We make those tubes, they extruded those tubes, and we grow the algae inside those tubes. And then we have to sort of maintain the algae culture using different technologies. But that is a representation of what a typical tubular system could potentially look like. And it would be easily cleaned with little sponges that run down the inside. and can be made into many, many iterations to be able to make this
So
system.
do you start with a little bit of algae, and then the algae expands as it eats the sewage, and then when the tubes are filled with algae, you harvest them and then start over?
Yeah, sort of. We actually harvest them continuously. So the algae are circulating through those tubes, and they circulate through what's called a gas exchange column. And then in the gas exchange column, we also harvest them. So we harvest them continuously. We add wastewater regularly, so we're sort of feeding them all the time, and they're growing and growing in the wastewater. We also feed them carbon dioxide, which, as I mentioned in the video we just saw, is a greenhouse gas that is really good to tie it up in algae rather than let it loose in the atmosphere where it's warming the atmosphere.
Now, do you pump carbon dioxide directly into the tubes, or is it just pulling carbon dioxide from the atmosphere?
We pump carbon dioxide into this column where we can exchange the gases. And this allows us to feed the algae with carbon dioxide that would otherwise go from something like flue gas from a chimney into the atmosphere. Instead of dumping it into the atmosphere, we feed it to the algae.
Does it take a lot of energy to run the algae farm? Because it has to produce more energy than it consumes, otherwise it's not very valuable.
Why, Marty, that's exactly the rub. You need to be able to get an energy return on energy invested that's greater than 1, or else why do it? And in the Omega system, we've integrated it with solar energy, and we've also integrated the idea of using wind or wave energy. But the solar energy is more than adequate to provide the energy that we'll need for growing the algae. And in that case, we can raise the energy return on energy invested above 1.
Is there any specific kind of algae you use which is superior for this purpose than other algae? I mean, do you have to pick the right algae?
Yes, that's true. We want to get the right types of algae. We have actually just used algae that grow naturally in the wastewater. And keep in mind that our system, the Omega system, is a freshwater community of algae living inside those tubes, and they're surrounded by seawater. So if our system leaks, the algae die in the surrounding water, so they can't become invasive species in the marine environment. So we're not too partial about what algae grow in our system, as long as they grow on wastewater and they die in seawater.
What are the remaining technical problems that have to be solved before this can really be rolled out as a working project?
There are a number of problems. The biggest problem, though, really is scaling. And we need to test this at larger scales. The Omega system that was tested as a NASA project and a California Energy Commission project was only done up to about 450 gallons. We need to go to thousands and even millions of gallons. And that scaling issue needs to be resolved. There are many other social problems in terms of, so where are we going to be allowed to do this? And what about wind and waves? And what about currents? And so we need to identify protected bays.
Well, you're right. You live next to San Francisco Bay. That would seem like a good prospect.
Yes, and there becomes another social problem. How do you get permission to use San Francisco Bay? And how long will it take you to get permits? And then if you did get permits, what about legal issues? And so what about litigation that people don't want a not in my backyard mentality? So we've been looking globally for solutions, hence the name, the Omega Global Initiative. And it could be that the U.S. won't be an early adopter because of some of these restrictions that are just legal issues.
Is it very capital intensive to begin with? I mean, it takes up a large space, but the basic materials seem fairly simple.
Yes.
A lot of plastic tubing.
Yes. No, that capital costs are reasonably low. The biggest hurdles that we have now have to do with building the offshore infrastructure and coming to terms with building a structure that's stable and robust in the marine environment. The biggest cost is not going to be the plastic. Pumps are one of the costs, but the big issue now is getting the first example, right? Once we build one, then everybody else will say, oh, we can do it better than that. And then we'll have a bunch of people trying to develop this technology. The reason this is important is to get a first example is because people want to be the first to be second. They don't want to be the first to be first. And if we had just one working example in a bay someplace, and where people could come and look at it and walk out on the pilings and look at the system floating and seeing that it's producing food and cleaning water and growing algae. And I mean, then I think a lot of people will get into this technology and the technology development.
Well, if you're looking for investors to help get this started and someone said, well, I'm interested in the technology, how much would it cost me to create one of these farms? What would you tell them?
Well, it totally depends on where we are. So there's a lot of logistics issues.
Well,
right?
let's say San Francisco Bay.
Well, we did an estimate for San Francisco.
Since we're already here and there's a ton of venture capitalists in this area anyway.
We did, okay, well, San Francisco Bay has its unique problems of getting permission to be able to work in San Francisco Bay. But when we did the techno-economic analysis, we were talking about a few $1 million to build a 1 acre system. That would be the capital costs. And then additionally, we'd need some operating costs. But think about what we're doing. We're potentially making a huge amount of biofuel. We're treating and cleaning the wastewater. We're providing habitat in the ocean, or at least in the bay. And we're looking at a sustainable system, a system that can be replicated all over the world to produce local sources of liquid fuel.
Well, everybody wants to be green these days, so you'd think that this type of thing would arouse a lot of interest.
It is definitely arousing a lot of interest. I've spoken on TED Global about this technology 2 years ago, and over 500,000 people have watched my TED Talk. In fact, your viewers can see my TED Talk. I think we can put up a link to it.
I think we have a slide somewhere that shows how to search for that.
Yes, good. Yeah, there's a big interest around the world in the Omega system, and I'm hoping that the system will catch on.
Now, who's developing the technology? Is it just you, or do you have a team of people who are working on it?
There was a team funded by NASA and the California Energy Commission that worked for 3 years to look into all of these technical details, and 2 students have doing their PhD thesis. One is finished with his PhD from Merced, and the other is finishing her thesis on the techno-economics of the Omega system. But now there is no funding for the project, and a global initiative is unfunded as well, but it's a group of volunteers, mostly students from UC Santa Cruz, who are looking into places around the world using Google Maps and data on the internet. And then we're trying to find people, once we have really good sites, people that are local people that work on wastewater or do aquaculture or interested in biofuels. And there's places all over the world that are expressing interest. India, all around ASEAN, China, Singapore.
I think people are looking for relatively low-cost solutions to environmental problems, and this sounds like it can solve a lot of environmental problems at once. Now, you're talking about taking the fresh water that's generated by the algae and growing food underwater. What kind of food do you grow underwater?
No, wait. So the fresh water that's coursing through those tubes that's wastewater that the algae are growing in is a completely separate environment from the marine environment underneath, where we're growing typical aquaculture species like scallops or mussels. We can grow abalone. You can grow fish. Marine species that are just taking advantage of the fact that we're building an infrastructure offshore. So we imagine this big marina that allows you to access an offshore environment. And now you build cages or containers, or you hang ropes or strings or something that allows you to grow shellfish. And the aquaculture industry is well established around the world. You can grow shrimps and such things.
I understand that some of the initial motivation for this was to provide recyclable materials for long space flights. In fact, we have a few slides illustrating that. Can we see the first slide in that series, please?
And so this slide is the space station, which is an interesting image in the sense that if you think about what it means to go out into space, the people living in space, in the space station, are totally reliant on solar energy. Obviously, there's not an extension cord that reaches up there. And the reality is that if somebody in the space station went outside without their space gear on, their life expectancy is about 15 seconds. Their blood would boil, they would be killed by radiation damage. And so the reality of being in space forces NASA to think through how to use resources very efficiently. The wastewater recovery system that's shown here is a modification of what was developed for the space station to recycle urine as drinkable, usable water. And that's what we're doing with wastewater for the Omega system.
Okay, and I think we have another slide in this series. Can we see the next slide, please?
And so this is a concept of what it would be like if we were to try to imagine
This looks
people
like
living on Mars.
the red planet. That must be Mars.
That's Mars. And so what would we do on Mars? Well, there's very little water available on Mars, and there's not an atmosphere to breathe, and there's no plants growing on the surface of Mars. And so we envisioned living underground, growing plants to make oxygen, changing the atmosphere so that we can breathe and exist there. But this represents an example of a resource-limited environment, which is really the basis of how the Omega project started. I think it's the next slide.
Yeah, we have one more slide in the series.
And this slide shows the kind of cycle where you envision what we would consider a waste product here on Earth, something that's recycled as food, water, or energy. Because waste products on Mars are more valuable than what we have, anything available in the environment. So what we consider something to throw away in space and on Mars are things that we absolutely have to reuse. And that's the fundamental idea behind Omega. The notion of building an ecology of technologies where the waste product from one part of the system becomes a resource for another part of the system. That ecology of technologies is what NASA's been working on in what they call life support systems. And that was the seed that really sprouted into the Omega project.
We just have about a minute left. Do you think that this is going to catch on? Do you think that people will say, wow, this looks great, let's put some money in it and get it going? Are you optimistic?
I am. I'm really optimistic because we need to make a change. And all indicators are suggesting that the next generation is on one of the most important thresholds in the history of humanity, the transition from hunting and gathering our energy to cultivating energy and using resources on our planet in a totally efficient way.
Well, I'd like to wish you the best of luck for that. We've got to wrap because we are out of time. I've been speaking with Jonathan Trent, founder and director of the Omega Global Initiative. Visit our website, www.futuretalk.net. For Future Talk, I'm Marty Wasserman. We'll see you next time.